Welcome, everybody. While we're waiting for our slides. There we go. Welcome back to day 2 of our summer school. We have an exciting day of learning about, focusing today on, well, you'll see in the next agenda, it's morning and I apparently need my cup of coffee. Let's start that over again. We'll start with all of our speakers today. We have an exciting lineup of speakers today for the second day of summer school. And let's go to the next slide. So today's goals are to focus on explainability and interpretability, and we're going to look at that through 2 different lenses. We're going to look at it through the risk communication and social science lens and think about how the users are thinking about those concepts, which might be different than sometimes how the computer scientists think that their users are thinking about it, which I find a very fascinating result. And then the second set of goals is that we're going to work on XAI techniques, and specifically attribution maps, which are going to be XAI techniques for deep learning, to understand the insights of what our neural network is doing. So we'll talk about different kinds of attribution maps and talk about pitfalls and how to interpret all of them. Next slide. So the agenda is very, very slightly different than it was in the online agenda, but we haven't changed any of the content. We just changed where a break fell. So this is our agenda for today, and I'm looking forward to learning alongside you about explainability and interpretability. And with that, I believe I'm handing it over to Anne or Chris or Mariana.
All of us, quick intros. Let's let Anne, do you want to jump on and say a quick intro, and then I'll say mine and Mariana can do it and we can take away with the activity.
Thank you, Chris and Mariana. Good morning. I'm Ann Bostrom from the Evans School of Public Policy at University of Washington, and happy to be working with Mariana, Chris, and Julie DeMuth in risk communication, and Andrea Schumacher.
Wonderful. Go for it, Mariana.
Hi, everyone. My name is Mariana Keynes. I am a postdoc working on this grant as well on the risk communication side of connecting users to AI.
Wonderful. And then my name is Chris Wers, also a postdoc on the TAI4ES grant, working on risk communication with Anne, Mariana, Julie, and Andrea. And so we're going to actually start off with a little bit of a warm-up. So we're going to dust off our skills on Slido from yesterday, and we're going to start off with a poll. So thinking about yesterday, what words/phrases would you use to describe trustworthy AI? So we'll let that, give a second for that poll to go live and throw some words in. I'm actually going to stop sharing so we can see results on this first one. All right, I got some coming in. Reproducible, reliable, ethical. User dependent, I like that one. Interpretable, understanding, transparent. All right, explainable, reliable. Good, it looks like we're gonna have some good times. We're gonna talk about reproducibility tomorrow, talk about explainability today. Transparency is great, nice, all right. Understanding, white box instead of black box. Uncertainty, we're getting unbiased, intentional, robust, interpretable, unbiased, great. These are awesome. Reliable is coming in. Okay. Okay, perfect. Things are going well. Got the right ideas, a lot of the key terms. And then we'll move on over and go back to a second poll. So the next one we're going to think about while the juices are still flowing. What was your favorite part of yesterday? You know, those lectures. That's just open response. What did you like? What was good? Day 1. Things that were fun. Were interesting, stood out, comes to mind. Ooh, Shapley values. Okay, nice. Good deal. Okay, social science, nice. That makes me happy. Just one of the social scientists. That's great. Taylor diagrams. Ooh, permutation importance is getting a lot of joy here. Monty's getting some good shout outs. Interdisciplinary, thanks. Okay, nice. Yeah, Monty's part specifically calling out. Great. Nice. Okay. Amy's presentations. Good. These are awesome. Interactive. All right, which is good because that's what we're doing again today. It's the same idea. All right. Awesome. The polls. Okay, good. All of it. That's an awesome one. You guys an emoji in the word cloud. That's great. Okay. Looks like everyone's getting warmed up. I like this. We're ready for another great day of content. And so I'm actually we're gonna hop back in and share my screen. now that we're warmed up and ready to go, we're going to talk about explainability versus interpretability. And with that, we're going to put our active communication juices back into this idea about explainable. That was actually in the definition for a lot of people, are the words you associate with trustworthy AI. So what is explainable AI? That's the first question we're going to ask here in the slide now, related to the content of today. What does that mean to you? And I'll stop sharing this again. We can see those answers coming in. What is explainable AI? All right, so that you understand what the AI has learned. What I learned last May, not black box, transparent. Understand why an algorithm performs as it does. Can understand where the answers come from. AI systems are interpretable, no features contributed. Humans can explain how the algorithm reached the results. Okay, model output can be tracked back to its inputs, can be decomposed. Okay, again, against being a black box, understanding the steps it takes to land a certain way. You know, the AI is predicting and what's deciding interpretable results. Quantitative, contextualize. Okay, great. We're going to hit on a lot of these ideas. So this is great. They're also coming in really fast. So being able to describe black box learning mechanism, reproducible by others. Another key thing we've heard, which we're going to touch on tomorrow. And Andrea is going to dig into that. You can understand, understandable. Yep, a lot of focus on understandings, simple, interpretable. Great. So it's interesting. We're seeing the word interpretable come up a couple of times in the explainable definition. Data inputs, how the model is trained, verification, great. Human-friendly suggestions. Okay, so thinking back to that user perspective. Those are great. And then I want to switch to the next question, which I'm not going to share the screen again for, but what is interpretable? So we've got the one side of explainable. What does it mean to be interpretable? So to see if we can, these are different. What is interpretable AI instead? It'd be interesting if you see the word explainable come up in these. Reproducible and understandable, okay, good deal. A lot of reproducibility. Again, good teaser for Wednesday's lectures. We're going to talk about reproducibility and replicability. Good amount. Human understandable, okay, nice. Key focus being on the understanding. Easily digested by the end user. Understanding the use, input, output, understanding the model without additional methods. Okay, that's an interesting one, right? So if you don't need XAI, it's interpretable. Kind of reading between the lines on that one. AI components are mappable to model results. It's robust, can be easily run by others, translate to domain knowledge. Explainable, easy for outsiders to understand, users understand it. Okay, great. Expected behavior gives unambiguous answers. Model of variables, okay, great. Understanding, yeah, a lot of focus on understanding. Predictable, understand where inputs are. Okay, awesome. These are great. Good deal. So I'm going to cut these off now. We got the juices flowing. And then what we're actually going to do is hand it off to Mariana to dig into these terms and see how close we all were with some of these ideas.
Yes, and by digging in, I want to acknowledge that this is only a, maybe not a 6-foot depth understanding, but we're trying to understand more of how these two terms are understood by practitioners and developers, as well as end users. So this table here on the left, this is from Monty Flora's paper that is in preparation. And it is about exactly like, what is the difference between interpretability, explainability, and how does that change based off of the different lenses in which you're looking at them? And if you just quickly look through some of these definitions, I'll read some of them. So for Glippen et al. In 2018, we have interpretability describes the internals of a system in a way which is understandable to humans. So that seems a bit on par with what we had in our Slido examples. And then also for explainability, that same article said, explainability models that are able to summarize the reason for black box behavior or produce insight about the cause of their decisions. So they are very similar terms, but they are more nuanced when it comes to applications, when you get into the mathematics behind if you're defining a model. And unfortunately, there's only partial consensus in the literature about what these definitions mean. And more importantly, that they can be treated interchangeably, as you've seen here in this table. And in our next slide, the Institute, so we have put forth some definitions that we think as a working definitions fit to distinguish these two. So for interpretability, this would be the degree to which a human can derive meaning from the entire model and its components without aid from additional methods. So this is the focus that you can understand what's happening in the model without aid beyond the model. So the model is, think of it as it's the whole package. You can use it as is and understand. Whereas then with explainability, that would be the degree to which a human can derive meaning from the entire model and its components through the use of post hoc methods. So such things as verification and visualizations of important predictors. So interpretability, that is where you can understand the components of the model without aid. The model is a standalone, but with the explainability, it's you need to have additional methodologies to understand what's happening within the model. And now we'll look to what actual end users think of this. So this interview process here that I'm highlighting is the same data collection that Chris Wers talked about yesterday, but just as a brief overview, that this interview was conducted with National Weather Service forecasters, and we interviewed 14 forecasters across the central, southern, and eastern regions of the US. And in that interview, we interviewed across the ladder, if you will, of meteorologists. So we had 7 GS 5 through 12 meteorologists, 4 lead meteorologists, and 5 science and operations officers. And in the interview, we covered topics about the perception of and attitudes towards AI and AI trustworthiness. And we also interviewed on the perceptions of and feedback about a specific AI ML convective forecast guidance. And you can see those 2 examples on the right. And in this next slide, I wanted to give a little bit more of a walkthrough of doing actual qualitative data collection and analysis. So the interview process, or the whole interview collection, if you will, started with 1, we needed to have an AI-based product to interview on. And then second, we developed very research-specific interview protocol questions that were paired with those ideas of what is trustworthiness in AI? What does trustworthiness mean if, say, you don't know a machine, an algorithm is AI or not? And then you step through and do actual interviews. And these are interviews, like I said before, with forecasters, and these were done virtually. And in doing them virtually, we were able to increase the people we were able to interview because you have reduced travel limitations in that sense. But also you can do both video and audio recording of what the interviewee is responding to, saying. And so in this interview, we collected transcripts that are then inductively analyzed. So inductive content analysis basically means that you are looking at the data laid out in front of you. And as you're reading the data, you're seeing what concepts and themes are emerging as repeated importance. And in that, you then collect to have these overarching themes. And this is what was done with the data that we'll be talking about through specifically with forecasters on interpretable and explainable AI. So what AI and ML, explainability and interpretability mean to National Weather Service forecasters. So note, these are end users of the product, not somebody creating the product. So the specific section of the prompt, the specific section of the interview had the prompt of, these are just terms that have been used in certain academic and developer circles, and we're trying to get a sense of what they mean to potential users. And note that there is no wrong or right answer. So for explainability, we asked, what do you think about the term explainability? What might it mean in this context of a new AI machine learning guidance being developed? Second, we would have for interpretability, what do you think about the term interpretability? What might this mean in that same context of a new AI and machine learning guidance being developed? And now we can walk you through some of the results. So for explainability, we had 2 themes that came out, and they were forecaster and guidance with explainability, And then forecaster, guidance, and others. So the notion of explaining the guidance to another person. And we have some quotes here to highlight this. So forecaster 10, when asked this question of what does explainability mean in the context of new AI, he said, can I explain what this model is showing to me to another forecaster? Are those forecasters going to understand it? If I need to explain this to a partner, can I explain what this model is showing in a way that they are going to be able to, in plain language, get them to buy into what they're trying to tell them? So basically, snippet here is, as a forecaster, do you understand what the model is trying to say? And are you able to translate that into language of your core partners? So that would be like the broadcast meteorologist, emergency manager. So can you translate scientific information into information that's understandable by your partners such that they can act on that information? And in the next theme is forecaster guidance and others is forecaster 5 said, less explainable would be if you gave us that background, and that background is he's referring to the interview information he was given, but just like so overly technical, using terms that forecasters are familiar with. So in this quote here, we have the first portion where they're laying out what you don't want to do for explainable. You want things to be concise and to the point. You don't want them overly technical, but then you also want the information you convey to be in terms that are familiar to what forecasters are understanding. So not only do you want end users in mind when you're developing a product, but when you're trying to explain the product or have it be explainable, are you explaining it in terms that are also familiar and understandable to your end user? And next we have forecaster 7. They said, I don't think we need like a 100-page manual. I know a lot of forecasters really do like to know the internal workings of everything they work with, but I think probably the best way is just to keep it as simple as possible. So again, this notion of we don't need a dissertation on it, but we do need to have the basics of understanding how it works and such that we can communicate it to others. And we also have forecaster 2. They said, explainable would also mean that it's easy for my partners to understand. Again, that point that we had earlier. Forecaster 1, one meteorologist could tell another meteorologist. So it's just not partners to external partners, it's internal to the weather office. Can you explain it to someone sitting next to you? Forecaster 9, boil it down to say, okay, here's the basic conceptual model. Don't overcomplicate this AI to the point where it's just not usable. And that last point there is, because something can be complicated to the end user or to say someone without the expertise that you would have as a developer, you want to make sure that you're putting the AI's best foot forward in an approachable way, and illustrated here. And so then next for our interpretability theme. So this only had one theme coming out of it, and it was the basis of good visualization is key to interpretation. And that visualization is both in the display of the information, but also the interactivity that you have with the information. And in forecaster 1, they said, I get frustrated when really, really good tools are hard to use for various reasons. Interpretable is something that has a level of ease with it in terms of analyzing the data, the way it's explained, the graphical interface, the ability to loop and go through time. So it needs to have an intuitive and useful way of displaying the data. So similar to what I said previously about putting the AI's best foot forward, is you want to make sure that the information that's being conveyed is actually accurate to what the model is representing, and not just accurate, but useful and can be used by a forecaster in their forecasting needs. Forecaster 4 continued this point with, can the forecaster interpret it quickly? Does it clearly meet the needs of what it's intended to help the forecaster, right? Can they get a quick assessment of what it means and what it's trying to predict? So not only do you want to be able to understand it and ingest it, but there's a time component. Can we understand it on a quick time scale? Because as we know, weather happens quickly, decisions need to be made quickly. Forecaster 2, they said, you have ensembles and how that's displayed. I think that would be important too, so that I can look at the entire realm of possibilities. So with this notion here, it's not just showing like a deterministic output or a single point, but be able to visualize the whole of what the different AI and ML models are producing. So let's step back and do some larger takeaways here. So for developers, there's a focus on understanding both how and why the model is working for interpretability and explainability. However, for forecasters, the focus is much more on utility of the model and the output for the forecasting needs, as well as the ability to have interpersonal explanation. And so forecasters discuss the AI and ML weather products, explainability and interpretability within the context of them being able to do their core function of their job. So one is the display of the model output is intuitive and it meets the forecaster's needs. Second would be the ability to explain and discuss the model output amongst forecasters. And third is effectively communicate the model output in understandable language to core partners.
So we have one closing point in this section before we move to another interactive activity, and that is Rudin's principles for creating a predictive model that's not a black box. So this team has come out with a set of principles that they published this year, and the point that was made here is that where the underlying distribution of data changes, which is called a domain shift, problems arise if people can't troubleshoot the model in real time. And this is really a lot harder with black box models than it is with interpretable models. Think, for example, of climate change, where the distribution of underlying data in the environment are changing over time. And the value of physics constraints, for example, in the context of AI models for weather. So the 5 principles that they lay out here are intended to help use AI models and interpretable models in the knowledge discovery process so that the user can help create new science, create advances in what we know about the environment. The first principle is that an interpretable model, machine learning model, should obey a domain-specific set of constraints to allow it or its predictions or the data to be more easily understood by humans, continuing this theme that Mariana just talked about. These constraints can differ very dramatically depending on the domain, and in the environmental context, the constraints that have been discussed most frequently have been physics constraints, but there are others. Principle 2, despite the common rhetoric, interpretable models do not necessarily create or enable trust. They could also enable distrust because you're allowing insight into the model. They allow the users to decide whether or not they want to trust the models. In other words, they permit a decision of trust rather than trust itself. Principle 3 is that it's important not to assume that you need to make a sacrifice in accuracy in order to gain interpretability. In fact, in this team's view, interpretability often begets accuracy, not the reverse. Interpretability versus accuracy, in other words, is in general a false dichotomy in machine learning. Go for both. Principle 4, as part of the full data science process, it's important to expect both the performance metric, in other words, how you're thinking of how well the model is performing, and the interpretability metric, how well people are understanding and have insight into the model, to be iteratively defined. So both of these will change over time. And for high stakes decisions, interpretable models should be used if possible, because they are more easily understood in the moment and can be you can troubleshoot them in real time. And that's what makes them important in these high stakes decision contexts. Rudin suggests both visualizations and interactivity as ways of allowing real-time interrogation of models for that reason. And I think it's over to Chris.
All right, thanks, Anne. So before doing the activity, I'd love to pause and see if there's any questions, because I know we got a comment in Slido that we're going too fast and we're ahead of schedule. So take some time. You have anything that's stickier you want us to talk more about, please put that in Slido and we'll do that. And I'm actually going to take one Slido question verbally now. So the question in Slido is good visualization is key to interpretation, both for display and interactivity, not inverting the TAI4ES definition. Which I think is interesting. I don't know, Mari, you want to tackle it or do you want me to go for it?
I'll give a little bit of not so much tackling it. I'll lightly kick it and then throw it to you.
Okay.
So my thought there was that the output of any model has to be visualized in some way. Are those numerical numbers? or is that a paragraph narrative, or is it a graph? So there has to be some level of visualizing the information coming out of the model. So I would say that it's not inverting it, but if excessive visualization, like say you have to post-process, secondary, then I think you're then having to have that additional help. But the question is, if that first attempt of visualization is enough to convey to, say, in our case, those were forecasters' definitions, to meet the needs of a forecaster, then I would say interpretability has been met. But if excessive lengths, and that's a question of like, what do we mean by excessive lengths? That would be the question of, is that not inverting the definition? Kicking it to Chris.
I think too, even the great response and one step further is we just asked open-ended, like, what does this mean to you? You know, what does this term that we're using a lot in the AI world mean to an actual end user? You know, so we weren't looking, you know, take your definition from, you know, XYZ source, and then we'll see how close they're compared. It's like, we're using these terms, just like we were talking about trust, and they have meanings, and people are going to interpret them, you know, pun intended in some ways, in different ways. And so knowing what we mean by them is it's not going to have necessarily the same reaction, or it may trigger different responses. So yeah, we might not have thought about visualizations as the key part for interpretable AI, but that's where a lot of people were going. You know, so understanding where we're navigating the user's understandings and perceptions and then their decision-making space, as well as kind of the terms that we're using and trying to navigate both between them. You know, so if we say, here's interpretable AI, to an end user, it may not be the same point. You know, so we're kind of navigating those different kind of language and communication potential barriers, if that makes sense. All right, we've got another one too. So why hasn't the logical definition of mathematical interpretability been adopted? Interpretability is a relation between formal theories that expresses the possibility of interpreting or translating one into the other. I don't have a great idea on that. I don't know if anyone else wants to swoop into those first. In your definitions group.
That seems like something Monty would be able to answer, but I don't believe he's on the call right now.
Yeah. We could think about using a formal definition, but in this case, we really are taking the user perspective on it. So interpretation is all about, can a person make that translation for themselves, right? So in some sense, the formal definition is certainly aligned with the sense of the research group.
Totally. We ran into a similar challenge with, we're trying to identify trust and trustworthiness in interview transcripts. And you can use a perfect formal definition, but in reality, it's a little hard to actually put those into words, or like, this is actually what trust looks like in real life, or this is what interpretability looks like in real life. So kind of balancing some of those is always tricky. Yeah.
And the nice thing about the work that showed up here and the principles that Rudin aligns with, the principles is that they align. So Rudin's group is working entirely separately and don't think that they've been doing user testing or anything, but they've ended up at somewhat of the same place, that they're feeling that visualization, for example, and interactivity are both key ways of allowing real-time interrogation and interpretability.
Perfect. I don't see any other Slido questions. I'm going to give it an awkward, 10, 15 seconds to see if anything else pops in before we go on to the activity. So these are really good questions, by the way. And it's nice to know what you're thinking of, and we can address those things as we go live. All right. Doesn't look like it. So I'm going to hop ahead. If you think of more, feel free to throw them in. We'll be on, someone from RiskCom will be on this whole time. And we can respond to those questions asynchronously. So this activity break, we're going to do a couple of different things here based on this visual, which is from Antonios, who will be speaking later, and you'll hear more about this. So if you don't understand it now, that's totally fine, but we're just trying to put some of these words into action and get your brain thinking about an applied example. So first one is, how do you interpret this visual on the bottom? And so theoretically, you should be able to go to Slido now, and it has the image there too. So if you need to see it, I uploaded it in both places. Answer that one out, and I'll stop sharing. So how do you interpret this? Antonio, I might call on you to actually see if some of these are legit or not, because I'm not going to know if they're good interpretations. There's areas of warmer temperature, blues are cooler temperatures, depending on the legend.
No, this is not exactly.
We'll give people a second though before you reveal the true answers.
Yeah, yeah.
Because then the other 14 people are typing will control back and then say the right, the right thing. Can't interpret it. Not enough information. Okay. Warm, cool zones. Okay. Red colors contribute towards and away.
That's more right. Yeah.
Red means connected to the prediction positively. So if they're at the South American coast positively, sea surface temperature anomalies. Ocean regions are contributing more. Regions are produced or forecast. I can't. I like that one. I'd be right there with you. There are biases in the model. We will find out. Need more information? Okay, good. Depends on the legend and the problem. Contributing positively and negatively.
Yeah, many people
You're
get it right. Many people, yeah, very good.
Okay, so then we're going to ask the next question. Okay, well, actually, we had enough people filling these in.
Heat map of contribution, exactly. Yeah.
Yeah. And so we're not going to answer out in the chat here, but we don't have to give the explanation yet, because the next question we're going to ask is, how would you explain this? Based on you got a couple little hints so far from the interpretability question, and where Antonios is guiding you a little bit. But we can flip, we'll give people a second to wrap these answers up. And then, yeah, how would you explain the same graphic now based on what you're seeing and your interpretation so far? How would you explain it? Heat map. All right. Can't. I'm right there with you too. Don't worry. That's why I pull Antonio. So how would we explain it? Okay, positive blue. It's negative. Can't do it well for references and values. Can't. Don't know what this is. By fitting a simpler model. Heat map relations with the locations. We need domain knowledge. Okay, all right. Writing on some good ideas. Heat map. Explain with information picture. I don't know. Options. No prediction. No explanation. Got your work cut out for you, Antonios, in the next section. We should do this again at the end and see how well you did.
Yeah, exactly.
All right, nice. Associated with higher, associated with lower, and that's all weakening and strengthening some global effect. All right. I think we're getting the sense of how tricky it is to interpret and explain, and then how to define these things when we try to put it to action. Then we're going to give a few more answers, some sensitivity analysis. All right, great. And so if we stop sharing this one, I'll go back and ask the next question just really quick, if we can share this. So looking at this map again, which regional oceanic basins had the biggest positive contribution to Y in this example? So that's going to go back to Slido. I'll stop sharing this again. That's our next question. So which regional oceanic basics had the biggest positive contribution to Y in this example? You can also select multiple too. There's a little bit of a trick. I don't think you're going to be able to, we can't see all of the options, we just see the top ones. Which I think is okay. You just see the winners. Antonios, what do you think about the winners so far? How do those look to you?
Yes, this is people are getting the correct answer. Yeah.
Okay, so we're getting correct answers, but we're still struggling with explainability and interpretability. But we provided a little bit more information, I think, in that question, which I think heats people into the right answer.
Exactly. I totally agree.
Yeah, so it's also an interesting exercise in thinking about how you talk about models, what we think about explainability, interpretability, and if it's first on face value with just a one model output of basic information versus if you have the developer hop on and give you some guided answers to it, it changes the ability for it to be interpreted or explained in some different ways. And so thinking about this, we're just getting your mind rolling a little bit, because this is what Antonius will cover in the next section. You'll get a lot more detail on this on the actual visual, but I want to pause and let people kind of reflect on this exercise. It's easy to say, why don't we follow that mathematical definition of interpretation? It's like, how would you have interpreted this following that definition? How would you apply that really distinctly? And there's a lot of those kind of real world, practical, user-focused ways that we use these words that are really important. So can you actually give a elevator pitch, 30 seconds, 60 seconds description of something to someone like this? And that makes a really big difference for the type of user. You say your user is not AI proficient, you have to meet them where they're at. And the fact that they can look at this and get the information they need to make the right decision is really going to change depending on that user context and what we're doing. And so that's also something we're planting seeds for the Trustathon activities. As you get into these different terms and a lot of these different ideas, thinking about how they actually are going to come across in that user relationship. Being able to explain it, being able to interpret those things. And with that, so we should be at a nice break point here. And we're a little ahead of schedule, but I'll share this just to show where we're at. And so it's now 9:37, and so we have a little bit extra time. And I know there's been some chat on how we want to spend this time, if we want to get rolling early or not. So let people pop on with their thoughts or just give an extra long break.
It's only like a 7-minute break, right? Just do that.
Yeah.
Because
Okay,
we have a long session coming.
Perfect. So we'll go ahead and take the break here, and we'll rejoin at 9:50. So we're giving you a little bit extra time with that. And in that meantime, feel free to throw things on Slido if you think of comments or ideas, and we'll either hop on and answer them a little bit earlier or just respond to them online in the replies. So take some time, settle in for it's gonna be a pretty, I think, long section of good, intense AI related information, and we'll be back at 9:50.
Yeah, so I wanted to add again, keep in mind that the next section is 80 minutes long, and we might have a break if we run well in time, but we might not. So use your time now, take a good 10-minute break, and we will see you again at 9:50. Thank you.
All right. See y'all then.
Okay. Welcome, everybody. Welcome back. I hope you had a nice break. Now we will continue our session with diving into the details of XAI techniques for deep learning. And in the next slide, we will first introduce ourselves. My name is Antonios Mamalakis. I'm a postdoc in Colorado State University, and I have been working for the last 2 years in exploring methods of XAI, specifically for environmental applications. Randy, do you want to go? Yeah.
Hi, everyone. My name is Randy Chase. I'm a postdoc working with Dr. Amy McGovern on a whole bunch of different meteorological and AI tasks. And today we'll be discussing some of the severe related XAI kind of examples as we go forward.
Hello, my name is Imme Ebert-Uphoff, and I am a research professor in electrical and computer engineering at Colorado State University, and also the machine learning lead at the Cooperative Institute for Research in the Atmosphere at CSU. And I've been working in AI for weather and climate for about 10 years.
Great. So before we start, we have a slide of the overview. So, yeah, the previous slide. Okay, we will start with introducing different the concept of XAI for deep learning. And the first thing we need to answer, the first question we need to answer is in the next slide.
And sorry, it was my mistake. If you want to do the intro slide, I am just getting a little mixed up here. Here we go.
Okay.
Do you want to start over on this one, Antonius?
Yeah.
Apologies, my fault.
No worries. So the way we have constructed this part of the session, we have constructed it in two parts. The first part, we will be introducing the concept of XAI. We will be talking about the motivation and why we need XAI, some opportunities that XAI tools bring in our field. And then we will dive into the details about four specific methods: gradient, input times gradient, the method layer-wise relevance propagation, and finally, the method sub-layer additive explanations, or SAP. The second part of our session will be is devoted to the introducing the concept of benchmarking XAI methods. This concept is essentially to introduce objectivity in the way we assess these methods before we go and apply these methods in problems that we don't know what the explanation should like. And then we conclude with some final comments and some big picture takeaways. So to start in the introduction of XAI, the next slide. The first question that we need to answer is, why is XAI necessary? And the answer to this question is very straightforward, because we as scientists, apart from caring about the prediction performance of a model, we equally care about making sense of the model and physically interpreting the model. And when we use models that are inherently interpretable, that's fine, but there are many models of artificial intelligence, like deep learning, for example, and neural networks that are not inherently interpretable. And this is where XAI is of use. I will highlight that more in the next. So if we have a linear model, even if the dimensionality of the problem is very high, we can even plot the regression coefficients, and then that gives us a straightforward way to understand the model. So in a linear model, independently of the definition of interpretability, a linear model is considered inherently interpretable with any definition that one might use. In contrast, on the other hand, when we are using a neural network, exactly because there are nonlinear functions in the architecture of the network, these nonlinearities make the algorithm of the network not non-transparent. And this non-transparency is essentially the main reason about why we cannot interpret the predictions right away as we can do it for a linear model. And that's why neural networks are considered black boxes. And this is where XAI comes into play. So what is XAI? In the next slide, XAI is a big umbrella term and includes all those methods that aim to give insight about the predictions of a deep learning model, of a neural network. Now, how do we do that? There are many ways to explain a prediction. One of the ways, and a very typical way to do that, is to provide heat maps, explanation heat maps or relevance heat maps that highlight which features in the input that the network used were the most important ones to determine the prediction. Let me give you an example in the next. So here is a simple example, and I'm using an example from an image classification task, so we don't need to get into the details of the, so everything is understandable to everyone. What we have here is that we have trained a neural network to classify images of different animals. And in this specific example, we have an image of a junco bird. Now, the network has correctly classified this picture as a picture that shows a junco bird. But then the question is, how did it do it? Then we can use an XAI method after the prediction. That's why we use the term post hoc explanations. We can use an XAI method to highlight which features in the input were important. So you can see here in this example, based on this XAI method, the eye of the bird was a very important feature that helped the network classify this image as an image showing a jackman bird. And this is, by the way, is a local explanation because it explains a specific prediction. Now, in the next slide, we provide some more examples. On the top, you can see different the different classifications that the network provided for the images. You can see the network input, and on the bottom, you can see the explanation heat maps. One can observe that in these examples, at least, the network seems to focus more on the edges of the body of the animal or the edges of the face of the animal. There are some features that are highlighted in blue color. This typically means that those features made the network less confident about its decision. And the features that, in contrast, the features that are highlighted with red color are those features that made the network more confident about its decision. In the next slide, this is a slide that highlights all these opportunities. Now, having these tools of these XAI tools, all these opportunities that these XAI tools bring to our field. And this is these are all the reasons that we should be excited about. For example, first of all, we have a well-performing model. We can calibrate our trust to that model. We can gain insight about how it makes decisions. And based on this insight, we can assess whether or not we should trust that this model will be equally well performing if applied in an out-of-sample prediction, task. Second reason why we should be excited about these tools. Using XAI can help us gain insight about why a model is not performing well. So we have a flawed model, and we can identify the reasons why it's not performing well. Where is it looking at to make the prediction, and why that might be wrong? This can guide us, optimize its architecture, and eventually get a better model. And lastly, XAI can help us learn new science. So we are in a prediction task that we don't know what to expect in terms of attribution. Based on those tools, we can gain insight about what the network has learned, and this can guide, potentially, this can guide us formulate new hypotheses that eventually will lead to us learning new science. So these are all the reasons, or some of the reasons at least, that we should be excited about these tools. Next slide. Okay, now that we have clarified what essentially XAI methods do, or what the aim is, let's take a step back and see, first of all, how many XAI methods are there, and where XAI methods fall under these three under the big umbrella term of AI models. As you can see here on the top, we have AI models which can be further decomposed into interpretable models and post hoc explainable models. Now, this separation was also discussed in the first part of the session. Interpretable models are models that their algorithm is transparent, so we can understand everything without the need of using a post-prediction method to gain insight. On the other hand, we have all those models that are black boxes, essentially, and we need to apply methods to gain more insight about them. Now, this can be further decomposed into global XAI methods. This was covered yesterday, and into local XAI methods. We will be talking about this today. Global versus local, the difference between the two is global XAI methods aim to provide insights about the strategy of the network for the whole data set. is a general decision-making process. That's their aim. Local XAI methods, on the other hand, they aim to explain what happened for a specific prediction. And these local XAI methods can be further decomposed into other categories depending on the aim of the method. But I want to highlight here on the bottom left this table that is from a computer science literature, Samek et al. 2020. This is a table showing how many local XAI methods there are out there. This could be 40 or 50 methods. So apparently, there are many ways to explain a prediction, and different teams around the world have developed their own methods about how to explain the prediction. Okay, I think now I will hand it over to Ime in the next slide.
Yes. So before we start diving into just a few of those methods, and honestly, only a few of those are used in our environmental science area, I just want to set the expectations for this. So applying local XAI methods, where you look at one sample at a time to identify the strategies a neural network has learned, is a detective game. So that's why I have this little detective icon here on the right. So you should only expect to get clues rather than complete answers. It's not a question of, oh, you have your neural network, which isn't explainable, you apply explainability tools, and here you need little nicely packaged up explanations. That's not how it works. You only get small clues, and you still have to put them together yourself. And it's usually a lengthy process where you try different methods, and you also try different samples, and you just have to find clues and put them together to generate hypotheses. So the domain expert is very important here, because without the domain expert, you can't do any of this in this field. Why is it lengthy? Again, because there are many different methods that tell you different things. And we get into some of those differences on Antonius's and Wendy's slide later. And because local XAI methods look at one sample at a time. Okay. Questions you will have to tackle when you do this kind of analysis is, which method should I use? And again, we try to give you a little bit of guidelines there. You should usually probably use more than one method, but still, you saw on the previous slide how many different methods there are. So you need to kind of figure out which ones are your favorite methods, what do they tell you, and how should you combine them? Number two, which samples should you look at? You can't possibly look at all the different samples in your training or testing data set. How do I ensure the results are consistent across other samples without looking at all the samples? So some samples, your attribution maps seem to indicate something, but does it generalize? Again, how should I interpret the results based on the fact that different methods give you different results? And we'll dive into that very deeply today. And if I use visual inspection of results, you saw these little images of the bird outline. It's like, how objective is it? Am I using wishful thinking when I'm looking at the results? So I think what I'm trying to get across is that this is kind of an art, and that it's not something that's quick. It takes a long time if you have one neural network and you want to explain it, and you just have to collect clues, and it's kind of an iterative process where the data scientist and the environmental scientist, if they're not the same person, if they're two different people, they have to talk constantly about what does this mean? Can we prove this? Is this a hypothesis? How else can we check our hypothesis? It's not a quick and easy thing to do. So the global methods have a much better chance of telling you things quickly, while with the local methods, again, they tell you things that you couldn't see otherwise, but it's a somewhat tedious, lengthy process. So don't expect to just get the answers to all fall out of there. It's a tricky process and it's a lengthy process, but we hope to give you some more clues as to how to use that. So in order to do that, we will first introduce a guiding example. That's a severe data set. And for those of you who are doing the Trustathon, about 1/3 of you have a severe data set as your main application. So for you, this might be helpful to use it for this, but I hope it's helpful for everybody. So we will use this application throughout the rest of today's presentation to demonstrate what XAI methods might and might not give you. So with that, I will turn it over to Randy.
Yeah, so for some context of the data set itself, it's always good to know what your data set looked like. So we're using this satellite and radar data set that was pre-prepared. And no, we didn't spell this wrong. This is the acronym that was chosen by the authors. So that we have a video here that should animate several times. So the data set contains water vapor, that's the leftmost image. The one next to that is infrared, the brightness temperature of infrared. And then the middle channel is the vertically integrated liquid. So you can think about that like radar reflectivity. Then the next one would be visible imagery. So that's just like the red channel, like our normal eyes would see if we took a picture from space. And then the last channel is lightning, that we have a special lightning sensor on the GOES satellite. So this data set was very comprehensive and great for machine learning. It's full of over 10,000 events with 4 hours tied into each event. And there's various different resolutions of each of these input fields. So the only issue with this data set is that if you actually look at its full storage space, it's 1 terabyte in size, which I doubt most people have 1 terabyte of storage available on their local machines. So it was a bit untractable for people to, or intractable for people to play around with and learn from these and apply these XAI techniques. So if you go to the next slide. So as a method, you might want to click outside the video. Yeah, there you go. As a method to make this data set a bit more tangible and easy to use, and potentially to use it on Google Colab or any other sort of environment, I've gone ahead and resampled this data set down into a lower resolution. So now you can see on the right here, it looks a bit more pixelated. That pixelation is because now we're going down to about 48 by 48 pixels. So this matches the lightning resolution. And now we've got it down to about 2 gigabytes in size. So it's a much more manageable data set, but it does lose a little bit of the information content that the original data set has. But it should still allow you to get your hands wet and figure out how to play around with these XAI techniques. So if you go to the next slide. So to set up the actual machine learning task that I trained the deep learning networks on, we're following suit from a paper I wrote this summer, well, submitted earlier this year, that looked at the traditional machine learning tasks. And in that paper, we asked the question of, does this image contain a thunderstorm? So right now we have the GOES lightning mapper, that creates our lightning measurements. But before 2016 or before GOES 16, we did not have this measurement. So envision a world where you could potentially create this measurement from the other satellite fields. Or imagine we're in a different part of the world where we do not have the GOES satellites, and we won't necessarily have these lightning measurements. So I tried to make these simple tasks for this machine learning example. So yeah, task 1, or the classification task, is based off of these images of water vapor, infrared, the vertically integrated liquid, and visible. Can you tell me if there's at least 1 flash of lightning within this 48 by 48 pixel image? And then task 2 is, could you actually tell me how many flashes are in that image? So these are relatively simple examples, and while they don't have all that power for operational use, I hope they're useful enough to give us a guiding example in this lecture today and in your Trustathon. So if you could go to the next slide. So just some perspective of the actual machine learning that we're using. I'm using a convolutional neural network. So you'll see here on the leftmost side is our 4 input fields or features. And then we have a couple, I think there's 3 total convolutional layers. So if you're unfamiliar how a convolutional neural network is set up, you usually take this convolution of the image or some sort of spatial weighting or a filter as you go through the image. So that's the 3 arrow lines. So that's the convolution. And then the single arrow is a max pooling, where we reduce the dimensionality of the features. And you'll see that we do this a couple times to get down into this low dimensionality space, so that CNN should be extracting relevant features to do the prediction. And then on the right is just a picture of a fully connected neural network, which is commonly appended to the end of a convolutional neural network. And you'll see that we have 1 single node as our output, which is either telling us the probability that there is lightning in the image, or it is telling us how many lightning flashes that the neural network is predicting for that. So that's for the classification task and the regression task, respectively. Go to the next slide. So one important thing that when you're training your machine learning models, you need to understand if your model is skillful. I think it doesn't help much to explain, well, Antonios made a good point that if your model is not skillful, it might be helpful to explain why it's not being not a very good skill. So that might give you some insight if there's a bug in your code or in your machine learning pipeline. But I think it's also always good to demonstrate to your readers of your paper or your presentation that, hey, we're trying to explain our model that's doing well, but here's how well it's doing first. So yesterday we discussed this performance diagram. So the x-axis is the success ratio, and then the y-axis is the probability of detection. And that blue line that's pictured on there is varying the threshold that we consider, yes, this image contains lightning, or no, this image does not contain lightning. And you can see that we're in that upper right-hand corner of the plot, which is where the ideal model space is. So this machine learning model is actually doing a really good job at predicting if there is lightning or if there is not lightning in the image. Meanwhile, on the right, I didn't have time to make the Taylor diagram, unfortunately, but this is a more boring way, I guess, to look at it, is just looking at the different metrics of the regression. So the numbers that are reported here are the flash errors, so bias or error. So you could see that for all of the data sets, our regression is about off by 27 flashes. But if we only look at images that at least contain one lightning flash, you'll see that conditional mean is a bit higher because we're not factoring in a lot of images that have nothing in them. So that I have 4 metrics on there, but you can feel free to look at these later if you're concerned about the actual skill of the model. And then one last slide here. So to tie in one of the global methods yesterday to give us some perspective before we jump into the local methods, I did apply the permutation importance technique to the convolutional neural networks. So you'll see an example of me shuffling the image on the top, and we go through, remember, we recalculate the skill of the CNN after we shuffle each one of the channels, and we recalculate the performance. So for the classification model, we're using the AUC parameter as our performance metric. And you'll see, and both of these diagrams are ordered in that the top bar is the most important feature, and then the bottom bar is the least important feature through this method. So you'll see for the classification example, the CNN is definitely latching on to the vertically integrated liquid, which makes sense as a meteorologist. Sometimes if you're watching the radar data, or if you're just a storm chaser, you can often see where thunderstorms are on your radar data. So that makes sense that it's using the radar data as its most informative predictor, say like 40 dBz, and maybe it exceeds a threshold and does really well. And I think that actually agrees well with Monty's results in his notebooks that he provided for this severe task as well. And what's interesting too is that as you go to the regression task, the vertically integrated liquid is still somewhat important, but the infrared is actually the most important predictor. And this could be, and one of my hypotheses that I had when I found this out, is that, so remember that the regression task is actually trying to predict how many flashes are in the entire image, while the classification task just needs to predict if there is one or more flashes. So for the classification task, it could be a little bit easier if I have 1 pixel of a VIL value of a certain threshold. While for the infrared and the regression task, it's more informative to know how much of the image has a cloud in it. And that could be, you would imagine a larger cloud structure would have more lightning flashes. So that's kind of my hypothesis of this result. But remember that permutation importance does have some drawbacks. So it'd be good to do the multipass permutation importance as well to do some more diagnoses of this model. So I think we'll one last slide here. So if you're interested in the XAI examples that we show in this presentation, I have a couple Google Colab notebooks that you should be able to go and recreate the images that we've created in these slides. And I believe Monty has adapted some of this for the GitHub repository. But if you want the exact images we have in the slides, you can go ahead and use these notebooks online.
And those notebooks were just posted in Slido as well.
Cool.
And they're in your slides as well if you want to see them later. But if you want to go now, the easiest might be just to click on the Slido links. And with that, I will turn it over to Antonios.
Okay, great. So now we have everything in place. We have our data set in place. And so now we will start diving into specific methods. Next slide, please. So before we start looking into the details of the specific methods, first we need to clarify an important difference between the concept of sensitivity and the concept of attribution. So there are methods out there, local explanation methods, that aim to estimate the sensitivity of the output to the input. This is an indication of the input or some features in the input being important if the output is very sensitive to changes in those features. So sensitivity refers to how sensitive the output of the model is when we apply changes to a specific feature in our input. This is the sensitivity concept. The attribution concept, on the other hand, refers to the fact that we try to estimate the marginal contribution of a specific feature to the output. In other words, what would be the effect of not having that feature that is of interest on the prediction? So these are two different concepts. We will start with sensitivity, but I want to clarify that even more. So I have here a linear model, exactly because a linear model is so familiar to everyone, so that we can crystallize this difference between sensitivity and attribution. So I have this linear model here only for predictors. I have assigned values to the weights and the predictors. And based on these values, we get a prediction, a y value minus 5.5. Now, if we were to explain this prediction from a sensitivity perspective, then what we need to do is to essentially think in terms of the weights, in terms of the regression coefficients of the linear model. That is the first partial derivative of the output with respect to each and every input features. From an attribution perspective, we would be looking at the contribution, that is the weight times the value of the input itself. So if we were to derive two different attribution, two different heat maps, one sensitivity heat map and one attribution heat map for this example, they would look like something like what you can see in the bottom right. And so you can very quickly see that these are different values. And so sensitivity and attribution is not the same either conceptually, but also not the same numerically. And then I think Ime wants to clarify this difference a little bit more from a different example. Yeah.
Right. Thank you, Antonio. So great job explaining it from the mathematical side. Just because it's a really important concept, I always like to explain things in different ways. So I'm going to just give you another way of looking at it. So I like to give the Warren Buffett example. And if you're not familiar with Warren Buffett, he's a very famous investor and he's super rich by now. And let's say you want to learn from Warren Buffett's investment strategies. There are different questions you can ask. So we're going to look at two different questions and ask which question would you like to ask. If you're asking the sensitivity question, you're asking about changes from the current situation. So given his current financial situation, and again, he's super rich already, right? So super rich guy, look at his current financial situation. You would ask which financial actions would change his net worth the most, either up or down. Right? So you're basically saying, okay, you have this super rich guy and you're asking, okay, for which kind of actions that he can take now, which ones would make him even richer or less rich? Let's just say which ones make him richer. That might not be what you want to know if you want to get very rich yourself, because you don't have all these resources that he has right now. But that is the question sensitivity asks. From the current state, what changes the net worth in this case the most, or what changes the answer the most? In contrast, the attribution question is more, how did he get here? Given his current financial situation, how did he get here, say, from the situation he was in 10, 20, 30 years ago? So it's asking a more global question. Still looking at the current sample, the current situation he's in, like what got him here from some base state 10, 20, 30 years ago. So there's no right or wrong question, but each question will give you different insights. So you need to use and interpret them accordingly. And Antonius is going to show you methods for sensitivity maps and for attribution maps. And so you just need to really be aware of the difference. In most situations, and maybe that person, maybe personally the case, but we usually find the attribution questions more helpful because they really tell you more about, okay, what was it that pushed us into the current situation? Rather than saying, okay, what would change my current situation the most? To bring that back to an environmental science application, let's now think about the severe data set. And let's say you want to identify a thunderstorm from the input. So you're use the same inputs, but you're trying to do a thunderstorm. Which question would you like to ask? The sensitivity question, again, is a modification of the current situation. Given you just identified a storm based on the inputs with certain confidence, what modification to the inputs would change this assessment the most? So let's say in the up way, you're given the current inputs, which pixels and which channels would you have to change the most in order to get the biggest return on bringing the confidence further up? That's a sensitivity question. The attribution question is, how do we get here? Given you just identified a storm based on the inputs for a specific sample with certain confidence, what are the most important reasons in the input to yield that confidence? So I hope you see the difference between those two questions. I will give you another example. There was a paper recently on identifying motorcycles in images. And it also asked a sensitivity question and attribution question. So it asked, okay, the sensitivity question was, what would I have to change in my input to make the motorcycle even stronger? And basically the answer was, well, add another motorcycle somewhere, right? While the attribution question basically asked, okay, what made this think that there is a motorcycle in the image in the first place? And so it gave you more of the motorcycle question rather than answering, rather than adding another motorcycle. So I'm hoping you get a little bit of the flavor of those two different methods. And with that, I will turn it back over to Antonius to talk about sensitivity methods. So again, sensitivity comes first, and then a little later we'll show you the attribution methods.
Great. Okay, so this is the slide that introduces the first sensitivity method. The name is gradient, and it's pretty self-explanatory. We calculate the gradient of the first partial derivative of the output of the network with respect to each and every feature in the input. And in this way, we get a sense about the sensitivity that of the output to the input. So it's the first method is called gradient, and it's essentially the gradient. Yeah, we'll see some results now with Randy. Yeah.
So here's some example, a relatively easy example, hopefully, from the severe data set. So if you look at these top images, I think that most people, even non-meteorologists, I hope, can see that there is a cloud in the image, and it looks pretty robust. It's pretty large size. So you can think of the X and Y dimension of this image of about 350 kilometers on both sides. So it's a pretty big cloud structure with some strong radar values. So that's the top row. And then the bottom row is this gradient sensitivity that we've calculated from the respect of the outputs, which I've put at the top in the red. You can see that the probability that this image contains lightning outputted from our CNN is actually very close to 1. So the neural network is very confident that this image has lightning. And then each one of the gradients for the respective input channels is shown in the bottom row. So you could see here that immediately it might look very noisy, and there's lots of strong blue pixels. So blue means negative sensitivity. So that means this area of the image I should change to decrease the confidence in the image that it contains lightning. And then red areas are positive sensitivity. So if I change that pixel and increase the value there, it'll increase the confidence that there's lightning. but you can see that this gradient image is actually quite noisy, and you have to almost take a step back and try to look at it for a little bit. And this was one of the concepts or key takeaways that Emma was noting earlier, that these are not straightforward often and take a bit of time for us to interpret. So you'll see that there's lots of noise. And then one thing you might not notice immediately is that the VIL channel looks a little bit more intense. You can see kind of the contrast. If you turn up the brightness of your screen you're watching right now, you can see that the contrast of that VIL channel, so the panel at the bottom row, third panel on the right, you can see that the VIL channel is a bit more contrast heavy. And these all have the same color scale. So that was trying to tell us that that has the strongest gradients. And that jives with our permutation global importance result from before, saying that the VIL for the classification example is the most important. So another way that's commonly done with these gradient methods is that we combine all of the different channels into one heat map. And those were like the images that Antonios was showing before with the birds and the dogs. So you'll see here, and the takeaway I want you to take from this is that it looks like the gradient here. So the yellows and reds colors are kind of where the image is the convolutional neural network is looking. So you can kind of see that the hotter pixels are loosely outlining the clouded feature. So that's at least confidence or evidence for me that the neural network is doing something right. It's confirming my belief that it should be looking at the meteorological feature in the image. So something I would be worried about is to say, hey, if that heat map just was a strong bullseye on a very dark part of the image, I'd be very concerned that there was a bug, or maybe all of my lightning images had a specific writing or annotation on it. And there are some pretty good examples in other fields, like diagnosing images of human lungs that have disease or don't have disease, that you don't want these unphysical explanations in your neural network. So this is all positive information that I'm seeing from this gradient calculation. So we go to the next one. So the previous example was a relatively easy example, and this is another easy example on the opposite end of the spectrum. So we're looking here at, if you look at the top input images, this is the same color scale as the previous. So you'll see there's basically nothing in this image. So this was part of the design of training the model here to do this task. We wanted it to not only see images that contain storms, we also wanted to see images that don't have anything in them, which is actually a large portion of a GOES or a satellite image. There are plenty of examples that don't have any storm in them, and it's just a clear atmosphere. So we again can analyze the gradients here, and it looks a bit more noisy. Maybe there is some sort of signal along the left edge of the infrared image. And this is a common thing with convolutional neural networks. You have to be not afraid, but you have to be alert to some edge issues. So when you take a convolution, in order to make the shapes of the convolution work out, sometimes we have to pad the edge of the image with a bunch of zeros. So what that can do is that can introduce an artifact or an artificial gradient along the edge of the image. And that might be what's being keyed in on this gradient image. But it also would require a much more depth in finding more examples to see if this was the case. So again, not very many things are exciting in this image, but that's by design. And it's good that the convolutional neural network is looking everywhere in the image. So you can look at the heat map and kind of everywhere it's looking, and not really any specific region is important to change the prediction. It's just kind of equal positives and negatives. So you go to the next example. So now we switch to the regression task. Remember, now we're looking at the CNNs trying to say, hey, how many flashes are in this image? So for context, I didn't put it in here and I should have, but this image actually had over 1,000 flashes in it. So the regression is getting close, not exactly right, but it's at least close. It's predicting 761 flashes in this image. But you'll see there's a pretty good contrast between the classification image, which was looking at mostly around the clouded feature, to the regression task that is now looking a bit more sporadically. So some hypothesis that I formulated when I saw this was, again, the regression task is a bit more challenging. We can't just look at to see if any one little cloud in the image is big enough to create lightning or strong enough of an updraft to create the charge separation that's required for lightning. Now, regression, you have to consider how much of the domain has cloud in it. So this is kind of my hypothesis of explaining why this gradient image looks the way it does. But I guess one positive thing or one encouraging evidence piece from this gradient image is that if you look at the heat map, it is kind of there, it's considering the edges of the cloud and some of the warm feature space or the surface. You can think about, a warmer surface would maybe mean stronger instability and more likelihood of storms. But again, we're grasping at straws and we need to look a lot more examples, but it's good to be thinking about a lot of these potential hypotheses. And I'm encouraged to see that the gradient isn't showing anything blatantly obvious that I don't want happening. So if you go to the next slide. Lastly, we show that blank example again to make sure that there's nothing nefarious going on. And it looks like, again, similar to the classification example, kind of spread out everywhere, no really specific pattern to an image that has nothing in it. So this is good. So one thing, I can explain this slide, Antonios, but one thing that you'll notice, and we've talked about, these images are very noisy. So something that is kind of counterintuitive, but a method that we should have cited on here, I can make sure we add that citation later, is that in order to smooth out that gradient, we can give slightly perturbed versions of the original example. So the idea here is that since the gradient is noisy, if we give slightly different permutations or changes of the same example, the noisy gradient pixels should be able to be averaged out. So it should create hopefully a more coherent gradient signal. So you'll see on the bottom right here, I've shown 100 different examples of the same strong convective example with slightly permutated noise throughout the image. And then if we take the average gradient across those 100 different examples, it'll hopefully give us a more smooth interpretation or explanation, sorry. If you go to the next slide. So this is the result. Antonius, did you want to say something? Oh, okay.
No, sorry.
Okay, I saw your window light up. I was just curious. Okay, so this is the smooth gradient result of that same convective example. Still quite noisy, unfortunately. So like Emma suggested in the beginning, there's really no silver bullet to this. Ideally, when I made this experiment, I was hoping, if you took an undergraduate meteorologist and said, hey, could you tell me if this image had a thunderstorm in it? I'm sure they would just outline the cloud and say, yes, this is why I think there's a thunderstorm in this image. Now, the convolutional neural network is doing this quantitatively and actually going through every single pixel value and considering these things. So it's a bit more complicated in what it's trying to do. But maybe there are some more encouraging things with the smooth gradient. You can see in the infrared image, it's outlining the edge. There's a strong positive sensitivity along the edge of that cloud structure. But essentially, the conclusions are similar to my previous analysis of this, is that it's generally outlining the edge of the cloud. And you can see the heat map is kind of centered on that. So you go to the next one, we can look at the boring, nothing in it example again, and you'll see that edge artifact kind of show up. And I think that's really from the zero padding that happens on some of the convolutional layers, or it could be that it's finding nothing in the image, and that's just what it highlights as sensitive. If we increase the value of the infrared there, it's going to increase the prediction because it's seeing warmer brightness temperatures in infrared. But if you go to the next example, again, we switch to the regression and the more sporadic or the more comprehensive sensitivity to the entire image. Again, maybe you can see here, if you're really trying to pull out signals, there's a strong negative sensitivity to the cold cloud tops. So if you look closely in the infrared, there's a couple really dark pixels of blue in there, and those are overshooting tops associated with strong convection, which are regions of source regions of lightning. So that's the updraft. And you can see how that really dark blue area, and if you look at the heat map on the right, is a really bright yellow color. So it's really looking closely at that updraft information to kind of, so if you change, so if I increased the brightness temperature there, meaning I made it warmer, so you made the cloud shorter, so it's not as deep as the cloud, so that would reduce its lightning capability. So that's how I would kind of interpret that. But again, these are, like Emma suggested, we need to look at more than just one example to come across as more of a broad scale decision strategy of the network. If you go to the next slide. Lastly, again, I apologize that this isn't all that, exciting and that it's not latching on anything super awesome in this blank image, but I was hoping to leave a lot of fun cookies or crumbs or fun examples you can find in this very large data set. There are plenty of good examples that I hope you all enjoy exploring later on. So I think that pretty good for coverage of the sensitivity example, and I'll be checking the slide out for questions and hopefully answering them in there for the sensitivity examples.
And I will add that there will be more exciting signals in some of the other XAI tools later on. So it's not all going to be as noisy as this. All right.
Okay, great. That was great. And now we're moving on to attribution. So now we will be looking at methods that aim to estimate attribution. The next slide. Yeah, the next slide here, that's a reminder to what we will be talking about. Attribution aims at estimating the marginal contribution of the input of different input features to the output. And motivated by this linear example, we can see here that a good estimation of the attribution is the gradient, the weight of the regression model times the input itself. Now, motivated by this, of course, this is a linear case, but motivated by this, in the next slide, we will be introducing the first attribution method, exactly because conceptually it's very simple. This method is very popular, and it's called input times gradient. Again, the name gives away all the information. Is essentially calculating the gradient that we already have when we want to estimate sensitivity, and multiplying that gradient with an input, with the value of the input feature that we care to estimate the attribution for. And now we will be going to see some examples of input times gradient.
Yeah, so hopefully this starts to build a bit of a story in your head. Now we've seen the sensitivity example, and now we jump into the attribution example here. And it is just as simple as this title explains. We take that gradient map and we multiply it by our input fields that we've seen here. So that's what immediately, something that caught my eye when I first started looking at this was that you'll see that the VIL and VIS, if we look at the input times gradient of those two input channels, you'll see that the cloud structure and the radar structure light up immediately. Right? And this is because the VIL parameter and VIS parameter, these are actually zeros. So zero VIS means there's no visible reflectance, and zero radar means there's nothing observed from the radar. So it really forces it to highlight or attribute that this part of the image is what's contributing to the prediction. The infrared and water vapor are a bit more convoluted, again, because now infrared is more continuous. The red regions here are not zero. In fact, these are the top end of the value of infrared brightness temperatures. Think about like surface temperatures of like 20 degrees C, right? While the clouds are more like negative 80 degrees C. So it's a more continuous field. Same thing with water vapor. So to interpret this, I think this is going coherently with our sensitivity results. We saw that the sensitivity of the image was very sensitive to the clouded area. And now our attribution of the image, you could see that the positive areas. So remember, to interpret this, the red pixels are saying, hey, this pixel is positively contributing to my prediction. So, these are increasing my confidence that there's lightning, and negative values are saying I'm reducing the confidence in my lightning. So you really got to get kind of close with the VIL image, because since it's so low resolution and the updraft radar structures are so much smaller compared to the cloud, like the anvil of this storm is much larger on spatial scale. So that's why you really got to get close to the pixel values. But you'll see that some of these red pixel values tend to line up with the red attribution values here. Similarly, again, remember my hypothesis before that, the machine learning task here is, does this image contain lightning? So the fact that some parts of the cloud contribute positively to that question, and then some parts of that cloud contributes negatively to that question is okay, because we just need to know if there's at least one flash in the image. So that's kind of unfortunate that the explanation is this noisy still, but it still is suited to do the task because we saw really good performance results. And this machine learning is doing something skillful to do this separation between images that contain lightning and images that don't. I think that's all the notes I have on this one. So if we go to the next one. Again, so since there was nothing in this image, you could see that the zeros of the vil, or at least they're not quite zero, because otherwise the input times gradient would be zero everywhere if they were exactly zero. But the input values are really, really small. Same thing with visible. You can see some hints at some small clouds there, or maybe very low clouds in the atmosphere, but definitely not tall enough to make any sort of lightning. And then you'll see that the infrared and water vapor here are attributing more to the overall prediction of this example. Go to the next example. Jumping back to the regression, remember we're looking at two different machine learning tasks. Similar to the classification example, it is, there are portions of the cloud that contribute positively to the prediction as well as negatively. So unfortunately, there's not this nice heuristic that it's saying, okay, the entire cloud structure here is why I'm making it. So us as humans have to step in and try to explain what these explanations mean. But again, similar results to before. And then lastly, if we go to the blank example again, similar answers to the classification example. So the reason I'm including these still while they have similar result, I just wanted to be thorough, and I want you to explore on your own. You shouldn't just assume that because the image has nothing in it, that the explanation will have nothing in it as well. So even though the classification example gives us evidence that the regression example probably won't either, it's always good to double check, because you shouldn't assume that the machine learning and neural network does exactly what you think it does. And that's, I think that's a good takeaway here, is to make sure you look at things rather than assuming. So I think if we continue on to those were our simple ones. So if we continue on, Antonios?
Yes, exactly. So this was the first simple attribution method, and now we will be moving on to more complex ones. In the next slide. Okay, the next one is layer-wise relevance propagation, an attribution method. So what we have here, let's say we have an input of a cat, as you can see here on the left, and we pass this input through the network and we get a prediction. The prediction about the certainty of the network that this is a picture illustrating a cat. What LRP, the philosophy of the LRP method is that then we use this prediction value and we start propagating this prediction value backwards through the network. And while we do this back propagation of the prediction, at each step we try to assess which neurons of the previous layer contributed the most to the neurons of the next layer. In this way, layer by layer, that's why it's called layer-wise relevance propagation, we estimate the relevance or the attribution of each neuron to the prediction. Now, if we keep doing that until we reach the input layer, this is essentially our heat map. And in this way, we, as you see in this example, we have identified that the network has focused on the bottom and central part of the image to identify that, to predict that this picture is a picture showing a cat. Now, how do we do this estimation of the relevance, though, this estimation of the attribution? If we zoom in, next slide, please. Yeah, if we zoom in this small part of the network, and so we have two layers, layer L and then layer L+1, and we are interested in identifying the relevance of neuron I in layer L. One way to do it, and this is known as the Lrp Z rule, one way to do it is to sum all the contributions that this neuron I contributes to all the neurons in the next layer, and each contribution is estimated as based on this fraction, where in the numerator we have the pre-activation from essentially the contribution from neuron I to neuron J, and at the denominator we have the summation of all these contributions from other neurons in layer L to this neuron J. So this is one rule based on the relative contribution of each neuron to the neurons in the next layer. However, next slide, please. However, there are other popular LRP rules as well. For example, the LRP alpha beta rule distinguishes between positive pre-activations and negative pre-activations. And the reason to do that is, in this way, we avoid having zeros in the denominator, which can make the relevances or the attributions very unstable. That's another rule, LRP alpha beta. And then I want to also highlight the LRP composite, which is a rule that combines the rule of LRP Z and the rule LRP alpha beta. So these are the three main rules that are very popular when it comes to LRP. Now I will hand it over to Randy. Yes.
So we didn't actually run LRP on our examples we showed here. Unfortunately, there's some issues with open source software being in wrong versions and the TensorFlow I used for our models that we trained above. But I found some examples in the meteorological readership and climate research that are similar. So this first example is from Centennial et al. in WAF this year. And there's a very similar task that's going on if you don't know what a UNet is, but we're doing image-to-image translation here. And the idea or the machine learning task is to forecast the future lightning flash location. So the idea of this machine learning model is to provide lightning guidance. So say in the next 20, 30 minutes, should I expect lightning in some region? So the top and the leftmost images here are the red, green, blue composite images. So we use 3 different wavelengths of imagery, specifically to give us perspective of depth of clouds. So these are not red, green, blue channels like the wavelengths. Specifically, we're using red for the infrared, and then the green channel is actually the red channel. Hopefully you're not colorblind like me, but that's kind of funny. And then the last one is a shortwave infrared channel. So how to interpret these is that the yellowish regions are parts of the cloud where there is glaciation. So glaciation is when we convert the water droplets into ice crystals. And this is important for lightning because we need ice-to-ice collisions in order to create this separation of charge and eventually lead to lightning. So that's how we're visualizing this here on the left. And then the right 4 panels are each one of the inputs to this UNet. So the leftmost input channel is the red imagery, then the 1.6, so that's the shortwave infrared, then the 10.3, which is a long wave infrared, and then the 12.3, which is another long wave infrared channel. So the way we interpret these is that the darker red pixels in these heat maps are more relevant to the machine learning prediction. And specifically, we're predicting for the center pixel. So the X value is saying, okay, based on this location, what information from the satellite is important for my prediction in that specific pixel location. So you see for the first example where the clouds are just starting to bubble up and grow, and there's some glaciation going on here in the brighter yellowish colors. You'll see that the shorter wavelengths, or the 0.64 and the 1.6 micron, and even the longer wave infrared are all kind of located, lighting up and near the clouds that are already glaciated. So that follows our meteorological expectation that the model is using close cloud relevant information to make its prediction. If we go to panel B, it's a bit more stretched out cloud patterns. I don't remember the exact example that they're showing here, but again, a similar interpretation is that it's looking relatively close to that center pixel, and you can still see some of the yellowish pixels. So some of the clouds are beginning to glaciate. And actually, if you envision the flow pattern of these clouds, it's looking a little bit upstream of the wind flow of saying, okay, maybe these clouds are advecting into my pixel labeled here X. And then the last example is interesting because there's this large kind of anvil cloud, that deep red color. So this is a big ice cloud that's just kind of sitting around from the previous convection in the day. But actually, there's actually lightning that happened later on and new convective growth. So if you look really close, there are some small cumulus clouds at the bottom of this image. And actually, there's cumulus clouds underneath that convective anvil. So what they're showing here is that the longer wavelengths can see or are attributing more to the prediction here of why it's predicting lightning for that specific center pixel. So it's kind of an interesting example. And if you want to read more, please check out Centennial et al. In WAF this year. So if we switch, I know not everyone's a weather weenie and loves lightning, like we've talking about lightning so far. So hopefully this climate example is a bit more exciting to you. So this is from Laib and Barnes et al. Well, Laib and Barnes in 2022. It just came out in GRL. And what they were looking at were these climate slowdowns, or I think a change in the slope of the, our climate is slowly warming if you look at the surface temperatures. And I think they're trying to predict regions in where the slope has changed and it's not increasing as drastically. So if you're interested in that, but please check out this paper. But we can look at the left-hand side is the LRP relevance again. So again, the brighter and more intense colors here, or the whitish colors are showing regions of the ocean surface that are relevant for this prediction. And then the right are the composite, or the mean of all the examples where there was a slowdown in the top, and then the bottom there was no slowdown. So you'll see that the machine learning is using different parts of the world's ocean to make these predictions. And I'm not a climate expert, so I would refer you to the authors of this paper and give it a read if you're interested in learning more about that neural network. So if we go to the next, go ahead, Emma.
Yes, thank you. And I entitled this slide Personal Notes because this is more like my experience over the last few years working with this. I wanted to give you I wanted to make sure that you don't just get the theory, but also kind of what's been happening in literature. So the first wave a few years ago was the really simple methods in our field. So in environmental science, first gradients, also known as saliency, and input times gradient, and integrated gradient, which is very similar to input times gradient. It's a slightly better approximation. They came first. So first, everybody was using gradient, or again, known as saliency, for the sensitivity. And then people started to use input times gradient, integrated gradient for attribution. That was the first wave. Then came the second wave. A lot of methods came in our lab, and that's again why I call it personal notes. In our group, we mainly used LRP, layer-wise relevance propagation. So you may have seen some of our papers. We were actually pushing LRP very hard because it had some advantages over input times gradient. But recently, now the LRP method is hard to run. And that's exactly why you didn't see results for the data set here, because now you have to go back to TensorFlow 1.x, because the current implementation is not compatible with TensorFlow 2.x. So it gets kind of tedious because you create your model in TensorFlow 2.x and you have to save it. You have to load it again in TensorFlow 1, and then you do LRP. And then not every model that you generate in TensorFlow 2 easily runs in TensorFlow 1. So it gets all complicated. And there's starting to be other drawbacks that we see for LRP for other applications too. So we still use it for some tasks. It's still helpful for some tasks. So we're not going to discard it, but maybe it's no longer a best go-to tool for your first thing. So the third wave is recently Shapley and DeepShap came out, and it has lots of advantages. It also has some drawbacks. So we'll have another slide like this with personal notes at the very end of this before the break in like 10 slides. But Antonius is going to kick you off now on Shapley values in a moment. But before we go into that, we have about 14 minutes left before the end of the session. I just want to let you know we have about 10 more slides. Take a deep breath right now, because Shapley is again heavily theoretical. So we have another 10 to 11 slides to go through. Maybe just take a 30-second breather. And if you have any questions, put them in Slido. I know we're not keeping up with all of the Slido questions. We will try to answer them all by the end of the session. But for now, let's just take a moment to breathe.
We're trying to answer the questions, I will add. But the problem is that sometimes the person best able to answer the question is the person presenting, and so they can't get to Slido. So just be patient. We swear we're all getting to the questions.
Okay. And maybe one question that came up in Slido that is very important is, you saw before with the input times gradient, that whenever the input is 0, the output will be 0. And it's a very good question of whether that's always a good idea. And that's exactly one of the things why we like Shapley. And so Antonius is going to talk about that. And also the question of what you use as baseline. So Antonius, I don't remember clearly whether you have slides specifically on baseline. I think you probably do, but if not, if you could talk about this either before the break or after the break and just put in some comments on that, that would be great too.
Okay, I don't think I have slides. I don't about the baseline, but I will try to integrate that.
Okay, great. With that, I will turn it over to you. So 11 more slides, let's go.
Okay, great. The last method of the last attribution method for today, the method SAP or supply additive explanations. So in order to understand this method, first, let's start by considering here equation 1 and considering this general class of explanation models that satisfy equation 1. This equation shows that on one hand, we have the network output, and on the other hand, we have a constant term and then the summation of the attribution values. Any method that can satisfy this equation, meaning any method that provides attributions that they can sum up to the network's output, is called an additive feature attribution method. Now, some of the methods that we already talked about, for example, LRP, fall under this umbrella of additive feature attribution methods. Now, however, in the next slide, there is an important theorem. And this theorem says that the only solution to equation 1 that satisfies desirable properties of local accuracy, missingness, and consistency, and I don't have the time to go through the details of these properties, but essentially these properties are desired properties that are required to be satisfied in order for the explanation to be consistent and be able to use for us to interpret the model. The only way to achieve that is when these attribution values are equal to the supply values. And the supply values are given by this formula at the bottom. I realize it might be a little bit overwhelming. I'll take some time to explain that in the next slides. But before I go to the next slides, I want to highlight that you can understand based on this theorem, we have now a theorem that says the only solution to this equation, the only way to provide consistent attribution is through supply values. And that gives a very important benefit to this method. It's very theoretically solid. There is a solid basis for this method. Now let's go and explain a little bit more what supply values are. Let's say, and I'm considering only a very small number of variables in the input, just for the sake, just for everyone to be able to follow. Let's say we have a prediction task where we use only 3 predictors, X1, X2, and X3. We have our model, our black box model, and then we have a prediction. And let's say we want to calculate the supply value that corresponds to this prediction and the feature X1. There are 3 steps. The first step, in the next slide, the first step is that we consider all the subsets of the input that contain X1. That would be the full set of the input, X1, X2, X3. next combination is considering X1, considering X3, but we consider X1 to be missing. The next combination is considering X1, considering X2, so considering X2, but having X3 missing. And the last combination possible is considering only X1. So these are the four combinations that of the input that include X1, the feature that we care about. Now, in the next slide, we have step number 2. In the second step, we try to calculate the importance of X1 for each and every combination that we consider in step 1. And how do we calculate that? We calculate the difference in the prediction when we consider the full model minus the prediction when we consider the X1 feature being missing. So in this first example, we consider the full model, all 3 inputs, minus the prediction of the model when we have X1 and X3 alone. And we can do that. We do the same for all the other combinations in the next slide. So we have established 4 differences, and each of these differences essentially represents the marginal contribution of X1 to the prediction considering different combinations of inputs. And the last step in the next slide, we take a weighted average of those quantities that we calculated in step 2. So the supply value of X1 is the weighted average of the marginal contributions of X1 when considering all the possible combinations of the input set. That's all. However, now you realize that in order for us to have a heat map, we need to do the same thing for X2 and the same thing for X3. And you can also realize that the bigger the input, the number of evaluations of our model that we need to do to calculate the supply values grows exponentially. And because of that, the algorithm that aims to calculate the supply values, it doesn't exactly calculate the supply values the way we saw, we described, but essentially approximates the supply values in a similar way to the LRP. So instead of propagating backwards the relevance or the attribution of each neuron, at each step we propagate backwards the supply values of the previous layer. So the deep sub, this is the name of the algorithm, is designed specifically for deep networks, aims at approximating the supply values for the entire network by propagating the supply values in a layer-wise backpropagation, similar to LRP. This is, I think, this concludes the description of SAP. And I think, yeah, now Randy.
And there was some discussion on SHAP yesterday, I believe, from Monty. So if you want to hear more too about that, about the formulation there. But jumping into some of our same examples that we wanted to visualize here, and we're looking at the deep SHAP results for that same first convective example. So I've added an extra row of images here, and that extra row is because the scaling here is a bit different between them. So the middle row, each image has a different color scaling. So the reason I did this is so we could see where in that specific channel the convolutional neural network is looking. But you'll see if we go to the bottom and we use the same color scale across all images, you'll see that the VIL SHAP values are larger in magnitude than the other predictor values. So this is a bit less noisy than the gradient examples. So you'll see there's more coherency to it. And it seems to be more identified around that cloud structure in specific, patterns of positive attribution and patterns of negative attribution. And it seems to be really focusing on the vil as the most important predictor, because that's one nice property of these SHAP values, is that their sum does, so if you take the sum of all of these SHAP values, so that's what I'm picturing in the bottom right, and if you take that sum and then add the expectation value, you get exactly the model outputs for that image example. So you'll see that the sum of across all channels, again, basically shows the vil field, essentially, and with some hints that the other fields are somewhat important for this prediction, but it seems to be mainly relying on the vil as the prediction skill, I guess, for this example. If we go to the next example, now in between these two examples, I'm not using the same color scale, but so keep that in mind, that the dark blue here doesn't necessarily mean the same exact SHAP value as the dark blue in the previous slide. And that might be something you might want to look at in the future to compare to two examples. But for these examples, I just wanted to look at just the specific example and see where in the image and which channel in the image is most important for the prediction. So for this one, if we just jump down to the bottom row, you can see that most of the water vapor, it looks like it's contributing positively. So it's pushing it towards that there might be more lightning in this image, while the infrared says the opposites, that there's most of the image looks negative. So maybe those two kind of cancel out. And then you see the vil is sporadic. And again, there's really no rhyme or reason to it, except that it's kind of centered. There's some more hot spot pixels in the center of the image if we look at the sum. If we go on to the next one, if we step to the regression task, you'll see if you look at the classification of the regression here, like we were seeing in the gradient methods, that there's a bit more information coming outside of the vil. But again, it's mainly reliant on that radar prediction or the vertically integrated liquid, despite the single pass permutation importance, saying that the infrared parameter was the most important. So it's kind of an interesting result of conflicting values. Let me see, I check my notes. I think that was all I wanted to say on this one. We go to the next. Yeah, the regression of the last example, again, you can see there's lots of blue pixels on the vil here contributing negatively or reducing the output SHAP value. So that's one cool thing that I really like about SHAP, is that you could say, yeah, there's more blue pixels probably than red pixels. I know this is very qualitative, but actually if you take the sum, you know, they're relatively equal. If we take the sum of all the SHAP values in that sum image, you see that's why our output prediction is relatively near 0 or 4 flashes. That's an interesting result. Okay, let's go to last. Yeah, so just as a reminder, all of these images that we've made, so if you're struggling with the Trustathon, you can lean on maybe some of the code in these notebooks and feel free to copy it over. So you won't be able to change the notebook exactly, but you'll be able to copy it and save it in your own Google Drive, and you should be able to play around and change things. I kept it that way, so we still have one static copy that does not change, and then you can go ahead and put different examples in and play around with it.
All right. I just want to make one more statement here that I think we didn't mention is, you know, in CITO, some people pointed out that most tools in computer science are targeted towards classification. And that's why we here on purpose demonstrate everything with classification and regression, because it's often not trivial to apply it. And so you see here that you can apply many of those tools for regression tasks. The other thing that I wanted to point out is, you know how Randy shows the 4 different channels, the output. You actually usually have to play around a little to get these tools to do that, because most of these XAI tools actually assume that you have an RGB image coming in. So they always think there's a red channel and a green channel and a blue channel, which is not what we usually have. We often have very different channels, and then certainly not correspond to red, green, and blue. So sometimes they only give you the sum, and you have to dig a little deeper quite often to actually get the separate results for the 4 different channels. So always remember that if you have several channels coming in, you want to split the output into the 4 different channels and not do what computer scientists do and only do the sum of it and assume that red, green, blue has something similar in it. Because for us, VIL is very different from, say, infrared, right? So you have to split it in order to get some meaningful results and not just go with the sum as you see over here. with that, we're running up against time, so I will go to the last slide. And also somebody asked, so what exactly is first wave, second wave, third wave? I want to just make very clear, I call this personal notes because these are just terms I came up with for this presentation, just to give you a feeling for this. And I will admit that our group has been leaning much towards LRP, while other groups use GradCam. So if you look at Amy McGovern's papers, for example, you see also GradCam and things like this popping up. I'm just trying to give you a broad perspective. So the third wave, just to wrap up, is Shapley and Deep Shap. It's becoming very popular. It has many advantages. It has, number one, a better mathematical basis than many other methods than LRP or input times gradient. And as you just saw for the severe example, it often delivers really nice, strong signals. Now, don't jump and just use Deep Shap. As you will see later, it's good to use different methods and then takes information together from those methods. You shouldn't just use only one. Always use several and then keep in mind what they do and interpret them accordingly. Just lastly, Deep Shap also comes with its own challenges. Deep Shap is very slow. It can be so slow that it might limit the number of samples you can look at. So that's one thing. It also has big memory needs. So we sometimes have like, I don't know, 10 different time steps and 4 different channels of a high resolution satellite image as a single sample as input. And if we do that, we can only have like 10 samples for the first step in Deep Shap, which is to calculate a baseline, which comes back to the baseline question before. So some of those tools that you saw before always take 0 inputs as the baseline. Deep Shap is much smarter. Deep Shap actually calculates its own baseline based on you giving it as a first step a subset of your training data. The problem with that is that if each sample is very big, as I just stated for some of our satellite problems, it's high resolution and many channels, then this first step easily runs out of memory if you want to have more than, say, 10 samples. But if you use too few samples, then the baseline and thus the results are not robust. So all I'm trying to say is if you have small imagery, Deep Shap is fairly easy to use. If you have very large images and lots of channels and maybe even different time steps that you're feeding in at the same time, you may run into problems. Don't be surprised. There are tricks around it. You can use first the k-means clustering and sample from that, but it's not that trivial if you have very large, if each sample is very large in memory. Nevertheless, it's rapidly increasing popularity. In fact, lots of papers that I see coming out right now use Shapley values. So it might soon be the most popular tool. And with that, it's high time for our break. So it's almost 11:15. Let's take a 5-minute break and be back at 11:20. Thank you.
Sorry, I did not think it was me who was talking. Okay, welcome back to part 2. I thought I wasn't talking till the end again. We're going to dive into the remaining half. This was called part 1 and part 2 today because it was all XAI on deep learning. Yesterday was XAI for traditional machine learning. This will be the end of the XAI techniques, and tomorrow we're taking a completely different tack. And I think that's it for me. Next slide.
Thank you, Amy. So for the last part of our session today, we will be talking about benchmarking XAI methods. So we gave an introduction about what XAI is. We dove into the details of some of the popular XAI methods. Now we will take a step back and try to think about objectively assessing these methods for us to gain insights about differences between these methods and relative weaknesses and relative strengths of these methods that we can use when we explain the neural network in a prediction task that we know nothing about. So in the next slide, I essentially try to motivate why we need to introduce objectivity in assessing these methods. So let's take a step back and reconsider again the example of the Janko pair that we saw in the very beginning of this session. So we have the input, we have the network has correctly classified this image, and then we use an XAI method to answer the question, which features are the ones that made the network predict what it did. And we get an answer that highlights the eye of the bird and the edge of the body of the bird. But my question here is, and something for all of us to reflect upon, is how do we know that this is actually correct? How do we know that these are actually the features that the network looked at? If you think about it, we don't know that because we haven't seen the data set that the network, we cannot practically see thousands of images that the network was trained on. And even if one could say, well, it looks reasonable, the eye of the bird and the edge of the bird could be a determining factor, I will push back to that argument too, because the human perception of the explanation is not a solid criterion. At least it shouldn't be used on its own to assess the trustworthiness of the Xai method in the first place. All right. So in other words, what I'm trying to say is that we trust these methods to be providing us the explanation, but we are not, there is no ground truth to assess that. We are a little bit in the dark here. The second that I want to highlight is in the next slide. You can see that apart from the fact that there is no ground truth, if we apply all the methods that we can get our hands on, and there are many out there, we get different answers. And some of the answers that we get are very different from one another. So, and remember, this is the same model and the same prediction that we are trying to explain. So what you're looking at here, the differences that you can see, for example, between integrated gradients, this is a more sophisticated method compared to the input times gradient. What you can see here, the difference in between integrated gradients and guided back propagation, for example, they highlight completely different features. And so this difference is only inter-method variability, if you will. There's nothing else going on. It's the same prediction, the same model. I will argue that this uncertainty in the explanation that comes from different algorithms is problematic because it can propagate and be a limiting factor for us to trust the model in the first place if we are not certain about where the model is looking at, right? That was the whole goal of the Xai, to gain insight about where the model is looking at. So my point is we need to introduce objectivity in assessing these methods and establish ways to gain insight about the inter-method variability that we see here. In the next slide, we will be providing a way forward to this, to address this. And this is through attribution benchmarks. Now, here I will be presenting the general idea of an attribution benchmark. And this slide is inspired by a prediction setting, a climate prediction setting, but the general idea, the idea of benchmarks is general. So what we are doing here, the first step is to create a synthetic input. This could be random numbers. In this case, this is random numbers, random fields of numbers coming from a multivariate normal distribution. So each map that you can see here in the top left is a random realization from a multivariate normal distribution with a specific spatial dependence. And these maps aim to represent sea surface temperature anomalies, right? So the dependence, the spatial dependence is similar to the spatial dependence that happens in observations, but the synthetic input that we are creating here it never happened in reality. It's synthetic, it's random. The second step is that we are using a nonlinear function that which outputs a scalar value given the synthetic input. So for each map, we have a scalar value which represents the response to this synthetic input that we created. And so now we have a synthetic input and a synthetic output, and we know that the connection between the two through this function f, which is a nonlinear function, but I don't have the time to go into further details. Now, step 3 is where things get more interesting. We pretend we don't know this function f, and we train a neural network to approximate, to learn this function f. And because this is a synthetic data set, we can create as many samples as we want. I have created here 1 million of samples. This is unrealistically high number of samples, especially for climate prediction settings. So we can create as many samples as we want, and then we can assume that the network has learned a very close approximation to that true function f, let's say f hat. Now, based on this assumption, we can use the ground truth of the attribution that can be derived from f directly, because we know actually the function f, and we can compare the explanations that we get from different Xai methods to that ground truth, to that prior estimate of what we expect the explanation looks like. And in this way, we have something to compare the Xai to. We are not in the dark anymore. And that's the big benefit of constructing a synthetic data set, that we know the relationship between the input and the output. That's the whole idea. And let's go forward and see the next, the example. And this is the example that we were asking questions about in the first break, before the first break of this session. Now I think it's clear, I hope it's clear to everyone, that because we know this function f, that is a nonlinear function that we use to generate the output, we know which features contributed and in what way to this value of y that we care about. So in this example, the value of y is 0.066. The prediction from the network is 0.0802. Quick note here, the network that we have trained to approximate function f explains more than 99% of variability. This is a very huge number for a non-linear function. So what you're looking at here is that the attribution, the true attribution. Red pixels are highlighted with red color, contributed positively to this value of y. Pixels that are highlighted with blue color contributed negatively. So if it was not for the blue pixels, the y value would have been even higher. And now we can see what Xai methods give to us as an explanation for the prediction in the next slide. So you can see again, very different answers. And so if we didn't know the true attribution here, we will be a little bit in the dark again, because we wouldn't be sure what the network is learning, how the network predicted what it did. But now that we know, we can gain some insight. First of all, gradient and smooth gradient. These estimate sensitivity, they don't estimate attribution. That's why they don't correlate at all with the ground truth of the attribution on the top. We knew that, or we expected that, but this is a clear example, and that's why we are including it, to make once again the point that sensitivity and attribution is not the same. They're equally useful, but not the same. The second thing we can notice very quickly in the next slide is that the deep Taylor and the Lrp alpha 1 beta 0, for example, these two methods provide only positive attribution. So according to these methods, all the pixels are contributing positively to the network prediction. And this cannot be true. And looking into the details of the algorithm of these methods, one can detect why, mathematically, why these methods by construction cannot distinguish between the sign of the attribution. And this is something that we wouldn't know if we didn't have this estimate, this prior estimate of how the attribution should look like. And finally, in the next slide, the four remaining methods, input times gradient, Lrp Z, integrated gradients, and occlusion 1. These four methods behave very similarly for this example, for this data set, and they behave very similarly to the ground truth. You can see all of these methods highlight the southeastern Pacific, this pattern of very high positive contribution. The Eastern Tropical Pacific also, they highlight the Southern Indian Ocean, the Southern Atlantic Ocean as contributing negatively. So there is big agreement with the ground truth. So that's the whole idea of benchmarking. Now, this was a regression task, and we were using a fully connected network. In the next slide, we are going to apply the same idea, but in a different data set. This is again a benchmark data set, but it's not climate data yet. It's anymore. It's inspired from climate, from a remote sensing application where networks need to be able to detect special patterns and shapes, but it's not climate data. So what is it? What we have here is that we have generated, again, a synthetic input of thousands and thousands, I think 500,000 in this case, images that contain circular frames, as you can see on the left here, circular frames and square frames. And the task is really simple. The task is for the network to classify the input image as to which of the two shapes, the circular frames or the square frames, cover more area. That's the simple task. And because this task is simple enough, we can derive our prior estimate of what the explanation should look like, what the attribution should look like. And this is what we do in the next slide. So for this specific input, the true answer is that the circular frame, because of its thickness, it covers more than the square frames combined. So what we expect, and the network has correctly made this prediction, this classification. And so when we try to explain this classification, we expect to see that for a zero baseline, for a blank image as a baseline, we expect to see the presence of the circular frame making the network more confident about its decision, and the presence of the square frames making the prediction less certain. That's why we expect to see what you see there in the right. Now let's go and see what the Xai methods give for this explanation. Again, different answers. You can see the noise in these four methods: input times gradient, integrated gradients, Lrp Z, and deep sub. Some of these methods, if you recall, in the previous benchmark, they were behaving the most consistent, in a most consistent way compared to the ground truth. In this case, because we are using a much deeper network, we get noisy patterns in these results. And the reason is a phenomenon called gradient scattering. Some people already highlighted that in the Slido. So the deeper the network, the more likely it is for the gradient to start resembling white noise, meaning it will be more noisy. And so for every gradient-based method, the results will look noisy. That's one thing that we need to keep in mind, the noisy gradients. Another thing that we need to keep in mind in the next slide is that, as we also highlighted in the previous benchmark, the Lrp alpha 1, beta 0, and the deep Taylor cannot distinguish between the sign of the attribution. That's a second thing, important thing that we need to keep in mind when we are applying these methods. Now, the next method in the next slide, Lrp composite flat, that's a composite Lrp rule that combines many different rules. We can see here that the results resemble essentially a coarser picture of what the true attribution is, or what the true attribution we expect to be. So if someone is interested in local accuracy, this method shouldn't be the first method to apply, let's say. And the last method in the next slide, LRP composite. This is the same as the previous, as LRP composite flat, but it doesn't apply any flat rule in the network. This is the most consistent one in this application. It seems that it provides the most consistent attribution to what we expect it to be. Now, the last thing that we did with this benchmark in the next slide is that we did an experiment. We considered the entire input, thousands of images of circles and squares, and we simply subtract the value of 1 from the input. So the pixels that belonged to the frames and had a value of 1 in the unsifted input, they now have a value of 0, as you can see on the right here, when we apply this shift of -1 to the entire input. So values that belong to frames right now have a 0 value, and everything else has a value. All other pixels have a value of -1. Then we modified the already trained network. We modified the first layer of the network so that the predictions, the final predictions, are exactly the same. You can do that. The math is simple. You just shift the biases of the first layer accordingly to incorporate this change in the input. And then we again use the same methods to explain the prediction, which was the same in the next slide. So what we see that some methods are sensitive to input shifts, and these input shifts could happen at any time we go from Kelvin to Celsius. That's a shift in the input. So it's very relevant for our applications. As you can see, many methods, input times gradient and many other methods, provide completely different results as to what they did before the shift. And looking into this issue, we found out that this sensitivity in this case is due to the fact that these methods automatically assign a 0 attribution to a 0 value in the input. And because in this case, in the shifted input, the frames, as I said, have values of 0, these methods by construction assign a 0 attribution to all the frames, as you can see. And we call that issue the ignorant to 0 input issue, because there might be applications where a 0 value in the input is very important for the prediction, and this method simply by construction cannot do it. Okay, to conclude in the next slide.
Before you go to the next slide, maybe we can bring in the question of baseline. Would it be correct to say that all the ones that have, well, I'll let you answer this.
Yeah. I think the issue of the baseline is another way to look at this issue, the ignorant to 0 input issue, is that this method essentially consider a 0 baseline by construction, and they are not flexible enough to be considering any other baseline. So that's another way to see that.
So it would make sense to use them if your baseline isn't at 0, if you're dealing with anomalies or something like this. But if you're not dealing with anomalies, you have to be very careful not to automatically assume that your input is 0.
Exactly. So if a user is interested in attributing a prediction considering a 0 baseline, these methods are suitable to use. But if they want to use a different baseline, these methods will be, by construction, will be considering a 0 baseline, and the user will be dissatisfied because the answers will not be making sense.
And that is honestly the reason why we are shifting over to Deep Shep. It's another reason, because it doesn't have that issue.
deep sub allows the user to define the baseline. But the points that I want to the audience to keep from this investigation and this benchmarking is that three issues came up in this investigation. The first was gradient stuttering, the noisy patterns in the gradient that make the results of XAI be very noisy, especially for deep networks. It can be very completely incomprehensible. The second is the issue that some methods have when in that they cannot distinguish between positive and negative attributions. And the third issue is the one that we just talked about, is that some methods automatically assume a zero baseline, or in other words, they automatically, by construction, assign a zero attribution or contribution to a zero value in the input. And this can be problematic in some cases. And then in the next slide, we have created this table with all different kinds of XAI methods on the left. Some of these methods we already dove into detail during this presentation. We give a brief summary of the method, and then we indicate whether or not these methods satisfy, these methods have the issues, one of the three issues that we talked about in the previous slide. We also provide some extra comments, but the important thing I think here is to see is that no method is optimal. There are many arguments for some of the methods to be in the first method to use, but I think this investigation makes clear that all methods might suffer from a specific issue depending on the application. So I wouldn't be talking about the optimal method generally in the XAI research or applications. A better way to talk about XAI is best practices of XAI, not which method is the optimal, at least in my view. And so in the next slide, I will conclude as fast as possible, so we have time for questions. The issues that the key take-home messages from the benchmarking is that because there are so many different XAI methods out there, I think it's to the benefit for our community to start engaging with benchmarks where we know we have an idea of the prior, of the ground, of the attribution that we expect to see, so we can understand better these methods, their differences, and we can derive best practices about when to apply which method under which circumstances. And now I will hand it over to you, Ima, to conclude the entire session.
Thank you. So I just have 3 more slides, but no worries, there's no math in there. Hopefully kind of taking a big picture view again. Our detective lady is back, because I want to remind you again, we're kind of going back to the beginning, right? Applying local XAI methods to identify the strategies of a neural network has learned is a detective game. I hope you saw that. Expect to only get clues rather than complete answers. As you've seen, it's a lengthy process. What you can hope for is finding clues to tell you about potential strategies. And then you can design tests to verify these strategies. So sometimes we see, oh, I think it's a cloud tops that give me an indication, or it's a cloud boundaries, or it's a lightning channel. So it makes sense to, once you have those hypotheses, to see, for example, modifying input images and seeing, okay, if I add more lightning in one channel, will that actually do what I think it does? So they are, and again, this is where the domain science really needs to come in and say, oh, this makes sense because, and then you test it on more samples and things like this. But there's never a proof. It's still just hypothesis that you have there. And you can never say that you found all the strategies of the neural networks. You found, hopefully, the most important ones. Coming back to the questions we asked earlier, which method should I use? Again, carefully consider which question you want to ask. Is it sensitivity or is it attribution that you're after? Look at the benchmark to see in the table that we just had to help you decide what is best for your application. Try more than one method. Don't just think, oh, and that's not always going to be Shapley. It makes sense to use several methods and then interpret the results accordingly. If there's one pattern popping up in this method and another one here, try to figure out why that is based on what you know about the different methods. For example, one having the zero input assumption, the other one doesn't. So based on that, you need to interpret the results, but use more than one method and see, especially see whether you get consistent signals across the methods. And also make sure that if you change something a little bit in your network or anything else, that the output is robust, that it isn't just one sample that shows you this and for one specific setting exactly of the model. Second question, which samples should you look at? We often select samples to show extremes. So we usually start with samples that produce the highest or lowest output. So if I'm trying to estimate how many lightning flashes there are, well, I'm going to look at the samples that give me the highest and lowest one in the real world, and I'm going to look at the highest and lowest one also for the neural network, and I will look at those. Which samples did the model perform the best or worst for? That's always an important one. You know, just look at it. What does it do badly? When does it do badly and when does it do well? And then see whether the Xai attribution gives you some kind of a hint why that might be. And often it tells you, oh, whenever I have strong lightning, it forgets about everything else or something like that. So that's the idea. Look at best and worst examples there. And then very, very, very important, your domain scientist, your weather or climate expert or environmental science expert will tell you which samples represent extreme conditions. So again, strong or no lightning, but you know, when it comes to storms, it's like, okay, what kind of storms are there? Let's pick some samples that represent those different storms and look at those examples. So that's very, very important. Next question, how do I ensure results are consistent across other samples without looking at all samples? First of all, you can't guarantee that ever with local tools. And once you have hypotheses, you can devise a test, for example, using synthetic data. We actually do that a lot. And by modifying existing samples, but again, it's still mainly hypotheses. Work with your domain scientists to see whether this makes sense. Try to come up with some tests to convince yourself and others that this is actually the strategy that it's really using, that you didn't just see in a few examples and jump to a conclusion. How should I interpret the results? Interpret the results as clues, as hypotheses to be tested. Again, environmental science needs to be the core person interpreting the results with the help of the data scientist. The role of the environmental scientist is probably bigger than the one of the data scientist to make sense of what you're seeing here. And least but not last, this is maybe the most important point. Remember, the output of all of these Xai methods is an image. The image needs to be interpreted by a human. And there's a lot of potential for confirmation bias. I know that for myself, I want to see these patterns. So I have this wishful thinking that I want to see patterns. And so I see them. And then I have to really make sure that I'm not cherry picking. I'm not just taking a few samples that show these trends and other maybe don't, right? So again, if we treat our results as hypotheses rather than firm statements, we have the right mindset to interpret them accordingly. Try to confirm with other means. If you can design experiments to test your hypothesis, but that isn't always possible. But just be critical towards what you're seeing. Kind of have to explain it to another person, have another person critically ask, well, how do you know this is actually true? And again, try whatever you can in terms of looking at more samples, or changing your input a little, say maybe increasing lightning, reducing the lightning channel, something like that, to see whether you get the same, whether that confirms what you think you're seeing. Again, see it as hypothesis. And with that, here's some online resources. These are some of the packages we've used. Here's the notebooks. And then in the chat, I would like to point out Evan Krell. His research group has come up with a great petition chat package that I also want to recommend, and I apologize for not having that on these sites. With that, I will show you all the references, but you have some in all the sites anyway, which you can download from the agenda. And with that, we have time for questions. So does anybody want to pick any questions? And that's opening really up to everybody. Anything you've seen in Slido, everybody who's presented, of course, can just unmute and now talk about anything they've seen in Slido that they want to just discuss a little more with everybody. Anyone?
You
Any
want to
takers?
also, while you wait for that,
Uh-huh.
talk about the agenda, because I know that I'm supposed to be closing. Do you want to just remind people what we're doing tomorrow? And then
Sure.
you can do that while you wait for questions to appear. Or do you want me to do it?
Yeah, go ahead, Amy.
Okay. Well, this is, there we go. I had to get my camera on. This is just the standard thank you that we very much appreciate everybody who has been helping with this. And so that part, you can go to the next slide, because I think we have this every day. I just want to remind everybody that all of our sponsors have been fabulous. What I wanted to do, next slide, when it appears.
I'm trying. For some reason, it doesn't want to go to the next slide. Don't ask me why.
Okay, well, I'll just go back to your question slide and I'll just remind people what we're doing tomorrow. How's that? That's all I was going to do. So while we're waiting for questions to come in, the reminder of what we're doing tomorrow is that we are going to be talking tomorrow a lot about data and the relationship between data and trust. So there'll be discussions about the reliability and the trustworthiness of the data, how they affect your AI and machine learning models, and also a good discussion about case studies. So go ahead and just go back a slide and Emma can moderate all the questions.
Okay. Do we have anybody from the speakers who wants to answer anything? Well, while we're waiting for this, I see one question here in the chat. What is the extension of integrated gradient with respect to input times gradients? So input time gradient, I think, came first. And then people realized, well, okay, so you know that the baseline for input times gradient is that your input is 0. And input times gradient doesn't takes the trajectory of getting to the input into account. Antonius, can you explain that better?
Yeah, so that's mainly the issue with the input times gradient. The two main issues is, first of all, it's linear. If something is not linear, we can not assume that the gradient is constant. So the local gradient is not a good representation of the average gradient. And the other thing is that the input times gradient, by definition, will assign a 0 to any feature in the input that has a 0 value. And so that means that it considers a 0 baseline to explain the prediction. Integrated gradients, on the other hand, solves both of these problems. First of all, the user can define the baseline they want the explanation to correspond to. And second, the integrated gradients, this is where the name comes from. It calculates the gradient across many points from the baseline to the input, to the current input that we are considering, and then considers the average of those gradients as a representative gradient or sensitivity, and then multiplying that with the distance between the baseline and the current input. That is a better way to attribute the prediction. Another thing I want to mention about integrated gradients is that it satisfies the local accuracy property, the same property that supply values also satisfy. This property is also known as completeness. There are many different terms out there. So this property essentially means that the summation of the attribution that this method provides adds up to the difference between the current prediction and the prediction of the baseline. And that's a very valuable property to have. So yeah, these are the main differences between the two.
All right. One question got a lot of upvotes is this general question. How do you answer a client who distrusts the interpretability and reliability of results because, where we go? Oh, here. Because they see there isn't an optimal local method, but a few methods output similar but varying results to their question? That is an excellent question. Any takers, Chris?
Yeah, I think it's a really good question. And there's kind of two ways I'm going to address this. So first off is if you can communicate that well and it meets the user's needs, like, okay, say it's with the predicting a storm mode or something, and this is what I have my mental model and my forecaster look at storm mode all the time, and this is not, your explanation or your interpretation of what the model is doing doesn't match how I would think that you could do this well. Like that is not maybe a good fit. And maybe that's not a model this forecaster needs to use. And I think that's also an okay thing, is that if you don't trust certain things, we're not making sure everyone has to trust everything. Like it may not be the best pairing. Because we talk about this a lot with human AI teaming, is like our goals are aligned. It's like you're using the same kind of ideas I am to get at a similar thing so I can trust you. And so that might just be the first point, is you don't need to use that one or suggest different ways, or you think about that model if it can meet a user's needs in a different way. So it may have some variation, and that may be tolerable for certain tasks. Looking at rough placement or timing of a storm or different tasks, but some may not have room for variance. It might not be okay that the answer changes a little bit. So again, it might not be paired for that task. So communicating when it should or should not be used is going to be key. And so you make sure that those kind of not necessarily quirks or differences in the model are really well communicated and they're really well calibrated to the user's needs is going to be key. And then in the end, knowing that you don't actually have to like make everyone trust every model is also an important factor to that.
All right, thank you. The next one up here by Evan Krell, I would encourage everybody to click on the replies to that, because Evan was so kind to put his paper and the GitHub repository in there. And again, they're really good. So do click on that and copy over those links and play around with that. All right, we have 2 more minutes. Our time series data. And I don't know what you mean time series and spatial temporal, both space and time, or just time. So I would just answer it based on space and time. I mean, if you have a neural network that also has different time steps in addition coming in, then you can actually split it up across the different time steps and see, did the neural network pay the most attention to what happened recently, or 10 minutes ago, or 20 or 30, if that's all part of your input sample. I don't think I have a lot of answers if you have time series. I don't have much experience with that, I would say. You can use some of those methods. You would just get, if you say have a scalar time series, you would get the different time steps instead. So you would get a vector instead of an image. But I don't know, does anybody else have a better answer to this? Okay. In the 1 minute wrapping it up, I would give 2 comments. One about the bottleneck and latent representations. Yes, people are starting to look at that. There's a research group at UC Irvine. That's Mike Pritchard's group. There's also a group by Liz Moyer. She's looking at that, and a lot of that is looking at variation autoencoders. One of the issues was looking at latent representations, and if you have satellite imagery, you don't really have a slim bottleneck. So that makes it hard. And then the only other one that I wanted to answer was, excuse me, how to test a hypothesis. So we do that a lot with synthetic data, that we set up something synthetic. For example, we have a rotating storm, and we look at, okay, how does that storm, we kind of take the input image and we just rotate it around and see how, whether, for example, our neural network responds differently to different directions. And so we can set up all kinds of nice synthetic experiments once we have synthetic data. So if that's possible in your application that you generate some kind of synthetic data, you have full control over what the neural network sees, and there's no noise and all these things, but I realize it doesn't always work. Amy, did you want to add something, or do you just want to wrap up?
I was going to wrap up because I remembered that I was supposed to announce something and I forgot. So the thing I was supposed to announce is that the next day's blog posts and everything like that for the Trustathon will be online by 1 p.m. Mountain Time. So remember what time it is right now. It is noon Mountain Time. So you have an hour, and then all of that will be online. Thank you all.
Thank you
We'll
to all
see
the
you tomorrow.
speakers. If you want to turn on your camera one more time and wave. Thank you for all the questions.